So hello students, this is our second topic, and in this video, I am going to talk about the concentration units. Not all, but two of the very important concentration units which we use in physical chemistry, that is molarity and molality. These two are the very important concentration units which we learn in mole concept, the first chapter of chemistry, physical chemistry. But we uses them throughout the physical chemistry, which is about 50% of the ITJ syllabus. So understanding of these two are very important. I will discuss some fundamentals of these two concentration units and I will let you know the techniques how to manipulate them in chemical calculations. So the first unit is molarity. So let us know molarity, which is denoted by capital M. It is simply the moles of solute in 1 liter of solution. So if we have n mole of solute dissolved in V liter of solution, so molarity can be expressed in terms of number of moles of solute by volume of solution in liter. So it is mole per liter. Molarity is moles of solute per liter of solution. So this is the fundamental definition of molarity. So if we know molarity, if we know volume, we can multiply them. We will be able to find out the number of moles. So among these three, molarity, number of moles, volumes, any two of them are known, the third can be known. The first point is that in chemistry we deals with smaller volume, milliliter, and here the volume is in liter unit. So how to correlate them? Suppose we have been given a 15 ml 0.2 molar sulfuric acid solution. Molarity multiplied by volume gives number of mole. So for chemical calculation, we want to know the number of moles of sulfuric acid. So if we multiply molarity into volume, it will be molarity 0.2 multiplied by volume 15 into 10 raised to the power minus 3 liter. So now I have converted milliliter into liter. So it will be 3 into 10 raised to the power minus 3 mole. So if volume is in milliliter, this 10 raised to the power minus 3 factor will come again and again. So for this 10 raised to the power minus 3, we can write it like 3 millimole. 3 millimole. And usually it is written as 3 m mole. So this means millimole. So now we can say that if we multiply molarity directly to the volume in milliliter, we obtain millimole. And once we know the millimole, at a time when required, we can convert it into molarity also. So molarity into volume in milliliter gives millimole. So if we divide millimole by milliliter, we can get molarity and so on. So we work with millimole, milliliter, millimole relationship. Let us work out few problems related to molarity calculation. Suppose we have been given a question that A sulfuric acid solution, a sulfuric acid solution is 61.25% by mass and has density 1.6 gram per ml. Determine molarity. So what we have been given? We have been given percentage by mass of solute and density, and we want to know molarity. Molarity is number of moles of solute present in 1 liter of solution. So let us assume 1 liter solution and carry out all the calculation for 1 liter. So let us assume 1 liter solution, that is 1000 ml solution. Now if you could calculate the number of moles of solute in this solution, it will be molarity, since volume already I have taken 1 liter. So mass of solution will be volume multiplied by density. So 1000 multiplied by density 1.6, so it is 1600 gram. Mass of solute, it will be 1600 multiplied by 1.6 density, percentage. So mass of solution multiplied by 61.25 upon 100. If we solve, it comes out to be 980 gram. So moles of solute, it will be 980 divided by 98 molar mass of sulfuric acid. So 10 mole. 10 mole of sulfuric acid is present in 1000 ml 1 liter. So molarity is now 10, and we read it 10 molar solution. So when density is given, percentage mass is given, it is always better to consider 1 liter solution, so that the number of moles of solute calculated in 1 liter will be molarity of the solution. Let us take few more situations on molarity. Suppose a question is like this. Question is that you have been given a 2 liter 2 molar H2SO4 solution and a 5 liter 5 molar H2SO4 solution, and no water is available for dilution. What maximum volume of a 4 molar H2SO4 can be made? The question is that you have been given in laboratory 2 bottles. One bottle contain 2 liter 2 molar H2SO4. Another bottle contains 5 liter 5 molar H2SO4 solution. These two are the only solutions. No solvents are available. You can just take these two volume of these two solutions as per requirement, and you have to produce maximum volume of 4 molar H2SO4 solution. So for maximum volume, one can think of mixing the entire volume of these two solutions. In that case, the volume will be 7 liter. But will that give a solution of 4 molarity? Let us check. So if we make cases, mix the whole volumes. In that case, the mixing formula which we learn in stoichiometry in detail study of molarity, that when we mix the two solutions, the molarity of the final solution can be determined using the formula M1V1 plus M2V2 giving M3V3. So in that case, we will have M1V1 plus M2V2 is equal to M3V3. So M1V1 is 2 into 2, 4 plus M2V2 is 5 into 5, 25 is equal to M3 is to be determined. V3 is fixed, that is 5 plus 2, 7 into M3. So if we calculate M3, it will be 29 divided by 7. It is no way 4, it is greater than 4 molar. So if we mix the entire volume of the two solutions, we won't obtain solutions of desired molarity. Next, what can be done? We can take one volume completely and another partially. Since we have to produce maximum volume, we could be tempted to take the bigger volume completely. So in that case, let 5 liter 5 molar is taken completely and X liter of 2 molar solution. Now see what happens. Now once again, if we apply the same mixing formula, so M1V1 5 into 5, so 25 plus M2V2 2 into X 2X is equal to M3 final molarity. Final molarity we require 4, final volume will be 5 plus X. 5 liter of this, X liter of this. So it is 5 for 20 plus 4X. So if we solve it, 25 minus 20 is 5 is equal to 4X minus 2X, 2X. So X will be equal to 2.5 liters. So we will require 2.5 liter of this 2 molar solution. But the available we have is only 2 liter. So we cannot take 2.5 from 2 liter. So the only left third option is take 2 liter completely of 2 molar and x liter of 5 molar solution. So 2 liter 2 molar complete and x liter of 5 molar. Now if we apply the same formula, it will be 2 into 2 plus 5x giving 4 into 2 plus x. So it is 8 plus 4x. So x will be 5x minus 4x. X will be equal to 4 liter, which is possible since we have available 5 liter of this solution. So what is the final situation? Now that mixing 2 liter 2 molar with 4 liter 5 molar will give 6 liter 4 molar H2SO4 solution, and this is the maximum volume we could prepare from the given solutions whose molarity will be 4. So it is interesting. I have deliberately taken the first 2 trials which gave us a wrong result so that we could learn how it works. So next, let us apply this molarity concept to solve a question of stoichiometry. A question is that 60 ml 0.1 molar barium chloride solution is mixed with 40 ml 0.2 molar sodium phosphate solution where barium phosphate precipitates out. Molar mass of barium phosphate is given. It is 601 gram per mole. Determine maximum mass of barium phosphate formed. Determine molarity of sodium phosphate Na3PO4 and NaCl in the final solution. So this is an application of molarity in solving a stoichiometry of a chemical reaction. So let us first write the balanced chemical equation. Barium chloride will react with sodium phosphate Na3PO4 to give Ba3PO4 whole twice plus NaCl. If we balance it, 3 barium, so 3 BaCl2, 2 phosphate, so it will be 6 NaCl. Now, molarity into volume in milliliter gives millimole. So we have 6 millimole and 40 into 0.28 millimole. The stoichiometry is, stoichiometry is 3:2. So 3 moles of barium chloride require 2 moles of sodium phosphate. So 6 millimole will require 4. 3 requires 2. So 6 will require 4. So 6. So 6 of this will require 4. So 6 millimole will react with 4 millimole of sodium phosphate. So this is the limiting reactant, and this is more than 4. So this is in excess. So limiting reactant determine the amount of product. 3 millimole of barium chloride gives 1. So 6 millimole will give 1 by 3 into 6. So it is 2 millimole. 3 millimole of barium chloride gives 6 millimole of sodium chloride. So 6 will give 12 millimole. And 4 millimole of sodium phosphate will be reacted. So left will be 8 minus 4, 4 millimole. So 4 millimole sodium phosphate Na3PO4 left unreacted. Final volume is 100 ml, 60 plus 40. Now everything is done, just we have to do some multiplication. So mass of barium phosphate, mass of mass of Ba3PO4 whole twice will be equal to 2 millimole we have produced. So 2 into 601 upon 1000 millimole. So 2 by 1000 mole. So it will be 12 so 1.202 gram. Molarity of sodium chloride will be its millimole 12 divided by volume 100, so it is 0.12 molar. Similarly, molarity of sodium phosphate Na3PO4 will be its millimole 4 divided by 100. 4 millimole was left, so it is 0.004 molar. So that is the way to manipulate the molarity and all. So let us talk about another very important concentration unit, which is molality. Molality, which is usually denoted by small m. So molality is defined as the number of moles of solute in 1 kg of solvent. That is important. 1 kg of solvent. This is very, very important. Molality is defined for a given mass of solvent, not for solution. So it is the number of moles of solute present in 1 kg of solvent. So if n mole of solute in W1 gram of solvent, molality will be equal to number of moles of solute upon mass of solvent into 1000, since the denominator mass has to be kilogram. And I am emphasizing again and again that it is defined in mass of solvent. So molality is defined in this manner. Usually we need to correlate this molality with molarity. So let us see how it is done. We'll be doing this with the help of two questions which will give us some understanding about molality and molarity again. The question is, a H2SO4 solution is 5 molal 5 molal and has density 1.3 gram per ml. 1.3 gram per ml. Determine molarity. What has been given? Molality. And we want to know molarity. Molality is number of moles of solute present in 1 liter of solution, and molarity is number of moles of solute present in molality is number of moles of solute present in 1 kg of solvent. Molarity is number of moles of solute present in 1 liter of solution. Molality is given. So let us assume a solution which contains 5 moles of solute, which is molality. So if 5 moles of solute is present, definitely 1 kg of solvent is also present. So let us consider a solution containing 5 mole of solute, that is solution must contain 1000 gram solvent, since molality is 5 moles of solute in 1 kg of solvent. So now mass of solution will be mass of solute plus mass of solvent. So 5 into 98 plus 1000. So it is 490. So it is 1490 gram 1490 gram solution. Now this solution contains 5 mole, density is 1.3. So we can determine the volume of this solution. So volume of solution will be 1490 divided by density 1.3. So if we calculate it, it comes out to be 1146 milliliters. So now molarity, which is N by V, so it is number of moles, which is 5. So 5 upon volume, and we have to convert it into liters. So it will be 1146 divided by 1000. So 1000 will come in numerator, and if we calculate it, it comes out to be 4.36 molar. Here molarity is less than molality. Will it be true for all the time? No. It will depend on density. Density of the solution will decide which unit will be greater. Either can be greater. To illustrate it, let us see one more problem on molality. The question is, a 5 molar solution of urea has density 1.4 gram per ml determine molarity, determine molarity. Once again, more or less similar question, but I want to convey some information from the calculation of this question. So let us solve it. 5 molar. So once again, let us consider a solution containing 5 mole urea. Then it must contain 1000 gram of water. So mass of solution will now be equal to mass of solvent plus mass of solute, which is 5 into 60, so it is 1300 gram. So volume of solution will be equal to mass by density 1300 divided by 1.4 milliliter. So molarity, number of moles divided by volume. So it is 5 divided by 1300 divided by 1.4. So it will be numerator multiplied by 1000 since it is in milliliter. So it will be 14 into 570 divided by 13. So if we solve it, it comes out to be 5.38 molar. Now the molarity is more than molality, and that is due to higher density of the solution. So they are the fundamentals of these two concentration units, and I hope it will help a lot to the students in solving the stoichiometry problems. So thank you.